Okay, good afternoon, everyone. Welcome to the fourth session of algorithms. I'm Lin Lin from the math department at UC Berkeley. This afternoon we'll have 3 talks. The first will be given by Professor Andrew Zhao, and he's going to talk about entanglement accelerates quantum simulation. The floor is yours.
Okay, great. Thanks, Lynn. So it's a pleasure to be at QIP. So I'd like to tell you about this work on how entanglement can accelerate quantum simulation. This is joint work with my excellent co-authors, Zhao and Zhou. And there's a preprint which you can find in the archive if you're interested in reading more about this work. So the sort of take-home message for this work is that we can show better bounds on the cost of performing quantum simulation, specifically using product formulas, in the case where the state that we're simulating is entangled. And this is exactly the case where we want to be doing quantum simulation anyway, because the problem is hard classically. So let's get into it. So for this audience, probably you're generally familiar with quantum simulation, but just to set the stage and sort of motivate things a little bit, I think quantum simulation is something we should focus on. It's it provided the original motivation for the idea of a quantum computer, and I think it really remains one of the most compelling potential applications of quantum computers. It's relevant to things that we care about in practice that are hard to access with classical computers, or can be, and it's sort of close to the native behavior of quantum devices, so it's something that we can reasonably expect to do, maybe in the nearer term as far as digital quantum computation goes. But it really, I think, still is quite a challenging thing to implement. So while you maybe don't need too many qubits to do a Hamiltonian simulation that is classically hard, it's we seem to need fairly large circuits and fairly deep circuits to do classically hard simulations of quantum dynamics. So we really need to try to reduce the resource requirements for quantum simulation as much as possible. And at the same time, I think we should try to retain really strong theoretical guarantees on the quality of our simulations. One of the nice things about digital simulation algorithms is that we can really have, we can really sort of prove strong results about the error in our simulations and sort of have confidence in the correctness of our simulations, and that's something that we should really try to maintain. Okay, so what I mean by the Hamiltonian simulation problem for the purpose of this talk is really the problem of reproducing the dynamics of some Hamiltonian on a quantum computer. So we're given a Hamiltonian, we're given an amount of time that we want to evolve for, we're given some allowed error, and then there's an initial state loaded into the memory of our quantum computer, psi of 0, and then our goal is to output in the memory of the quantum computer the final state that you would get by evolving according to the Hamiltonian. For the purposes of this talk, let's just imagine we're talking about time-independent Hamiltonians, evolved for time t, and we'd like to reproduce that state up to this error epsilon. Of course, in practice, you have to worry about how did you get the initial state, what measurements do you make, but we're not going to focus on those kinds of questions. Now, the kind of standard notion of error that has been used in, I think, a lot of the literature on Hamiltonian simulation is this kind of worst-case notion of error, where we look at the maximum over all possible initial states for the simulation of the difference between the state that the simulation produces and the ideal time-evolved state. And this is, of course, nothing but the difference of the spectral norms of the ideal evolution operator and the unitary operator that the simulation provides. So we would like this difference of operators, the spectral norm of it, to be at most epsilon. And then our goal is to understand how expensive it is to produce such a simulation as a function of the evolution time, the error, and parameters of the Hamiltonian. Okay, so the kind of original proposal for how to approach this problem with a digital quantum computer goes back to a paper of Seth Lloyd from the mid-1990s. The idea is basically to use product formulas. So imagine that we've got some Hamiltonian. For the purposes of this talk, it's going to be we're going to be interested in like k-local Hamiltonians. So there's some natural decomposition of the Hamiltonian into a sum of terms, each of which are individually easy to simulate. And so the goal is just to produce the dynamics according to the overall Hamiltonian using the ability to simulate evolutions according to these simple terms. And so while these individual terms, of course, in an interesting case, do not commute, we can combine them using this idea of the Lie product formula that says if you go back and forth between evolutions according to the individual terms and you alternate enough, then you can get an accurate simulation. So that's true, of course, in the limit that you go back and forth arbitrarily many times, evolving for arbitrarily small time intervals. But you can really work out what is the cost of doing the simulation using a truncation to a given finite number of steps. So in particular here, we're seeing a first-order formula. And you can see that if you use this first-order formula to do a simulation for some small time t, you get a formula that's accurate up to order t squared. And then you can work out how many steps you need to get error epsilon overall. And what you find is that the number of step scales like t squared over epsilon. Now, if you want to do better, you can use higher order formulas. And for example, here's a second order formula, and you can actually systematically construct formulas of arbitrarily high order. So this was done by Suzuki even before people were thinking about using these formulas for quantum computation. And then you can work out the cost of a quantum simulation using these product formulas and find that it scales in a way that gets sort of closer and closer to linear in T in particular as you go to higher and higher orders. Okay, so this bound that's shown on the slide is one that is sort of a rigorous bound on the quality of a simulation, but it actually turns out to be quite a loose bound in practice, and you can prove much stronger bounds than this, and we're going to use those also in the work that I'm going to tell you about related to entanglement accelerating quantum simulation. So the idea is to make use of this idea of what's called local error analysis, which gives integral approximations or representations, exact representations of the error in terms of integral formulas. So for example, at first order, looking at the case where we have an evolution according to a sum of two terms, we have this kind of fairly simple formula that's shown on the slide. So this is just an exact way of implementing or of representing the error operator for a first order simulation for these two terms. And this immediately shows you, just applying the triangle inequality, that the error is upper bounded by the spectral norm of the commutator of these two terms that you're adding together times t squared. And this is really nice because there is no explicit sum over the higher order terms. Like we're taking account of all of the higher order behavior in this formula. And we see this commutator scaling, that we get this better performance that comes from the possibility of the commutator between these two terms maybe being smaller. These kinds of formulas we find can offer much better performance. They'll show better asymptotic scaling for some systems, and also in practice can really have much tighter constants. So this can give us much more efficient Hamiltonian simulation algorithms. Okay, and this idea has been developed in sort of a general theory that allows you to prove pretty tight bounds for fairly general classes of product formula simulations of Hamiltonian dynamics in terms of the following sort of result, which says that if you try to approximate the dynamics with a p-th order product formula, then you can show that the error scales like, well, definitely like t to the p plus 1. That's what it means for it to be a p-th order formula. But the coefficient depends on nested commutators of the terms of the Hamiltonian, the spectral norms of these quantities. And so you can work out from this what's the number of gates you need to simulate for a given time to a given accuracy. And again, this gives much tighter analysis of the behavior of product formulas and the number of elementary steps of the computation that you need to get a simulation up to some given accuracy for some given time. Okay. Now, I should say, I mean, this talk is really focused on product formulas. I should say that there are other methods for Hamiltonian simulation, like, for example, quantum signal processing, that perform better asymptotically. But I think product formulas, they're definitely very simple. They require no ancilla qubits. And especially for modest-sized problems, they're often really, I think, the method of choice. They will require fewer gates than these methods that scale better asymptotically. So I think there's definitely a regime where I think we should be interested in applying these methods, despite the fact that there are other kind of more sophisticated methods that perform better asymptotically. Okay. So now I want to think about if there are ways that we can actually do even better than this kind of theory of Trotter error analysis tells us these algorithms can behave. And in particular, let's think about whether we can take into account information about the particular input that we have in our problem. So if we think about doing quantum simulation in the worst case, the inputs for which we have the worst case performance could be very atypical. Maybe we don't actually care about those kind of worst case inputs. Can we do better if we have some extra information about the input state? And so it turns out that you can. And so one such result that you can give is the following. So we have this expression that I told you about before for the analysis of the error in these product formulas from sort of this theory of Trotter error. But if you assume that the input state is drawn from some distribution, and in particular So this would be a case if you choose the state, let's say, from the Haar measure, but you actually need a much weaker condition, which is that the ensemble of states you're interested in simulating, you're drawing the input state from a 1 design. If that's the case, then you can give a better bound on the error of the form that's shown here, where basically you just replace the spectral norm in the kind of theory of Trotter error analysis with this normalized Frobenius norm. And this gives you a bound which is no worse, like it can only be smaller, but it can in some cases give much better performance. And let me emphasize that in this analysis, we're not changing the algorithm at all, right? We're not coming up with another algorithm that's better for random inputs. We're just seeing that if in fact the input is drawn from this distribution, then the same algorithm that we wanted to use all along actually performs better. So if we were just doing something heuristic and sort of looking numerically at how it seemed like the error would scale, this is sort of what we would find. But this analysis really lets us get that from sort of lets us get a rigorous understanding of that being the performance of the simulation algorithm. Okay, so this is nice, but perhaps it's maybe hard to find cases where we really care about doing the simulation for a random input. The setting that I just described is, I think, fairly flexible. We only have this assumption of a 1 design, and maybe there are natural cases where you might care about doing simulations where the input is drawn according to a 1 design. But this analysis does require that you're choosing the input from some well-behaved distribution, and maybe that's not the case in some applications. You might care about a case where you don't have any particular nice distribution you're drawing the state from. Maybe you care about some particular input state that's the state you want to do the simulation on. So I think a natural question is, can we identify some specific features of states that we might want to do the simulation on that allow us to make the simulation faster? And we're going to see that we can do this again, sort of not changing the algorithm, but just really improving the analysis of the standard algorithm that we would be using. OK. So we're going to give some kind of a state-dependent error bound that sort of looks at how much error there is when we try to give this product formula simulation for some particular input state. All right, so the kind of observation that we make in this work that allows us to prove a better bound is basically the following. So we're going to look at the leading order contribution to the error. And this leading order contribution will really only depend on the marginals of the state that we're simulating on the leading order error terms of the product formula approximation. So let me say a little bit more precisely what I mean. So let's look at the operator that describes the error in the product formula approximation. Right? So in this expression, u is the normal u is the ideal evolution. This calligraphic u is the product formula. And we have these integral representations that we can use to write down this expression as some integral over operators. But in particular, we can look at sort of the lowest order contribution to that error, and that's going to consist of some local terms if we have a local Hamiltonian and we consider a product formula of some fixed order. So here we have these higher order terms, but if we just look at the lowest order, then we just have some local terms. Now, the locality of those terms will depend on the locality of the underlying Hamiltonian and also the order of the product formula that you use. These terms will basically be nested commutators of the terms of the Hamiltonian. So the higher the order of the product formula that you consider, the less and less local these terms will be. But they will be local terms of some constant locality if your underlying Hamiltonian has some constant locality and you consider a constant order product formula. OK, so now we want to look at the error, sort of what is the contribution to the error from these lowest order terms. OK, so the simulation order, to this lowest order, the error in that simulation will be approximated basically by the kind of sum that's shown here. We have a sum over these error terms. And what we're going to do is we're going to sort of add and subtract, like basically an identity inside this expression, right? So if we just look at one of these terms for particular values of j and j prime, this contribution only depends on the marginal of psi on the j prime subsystem. That's these are the system. This is the system on which the error operators j and j prime act. So we only care about the marginal of the state there. And we're going to add and subtract here this normalized identity, this maximally mixed state on that subsystem. So this is that term subtracted off, and here's that term added on. And now observe that this term that we added on over here, this is nothing but the Frobenius norm, the squared Frobenius norm, or the normalized squared Frobenius norm of those error terms. And this first term is something that if these marginals are maximally mixed, will actually be 0. Right? So if the marginals of the state rho jj prime are maximally mixed, then this is actually 0. And more generally, if those marginals are not maximally mixed, but they're close to maximally mixed, then this will be a small contribution, and the error will be dominated by something that has this kind of Frobenius norm scaling. So with this kind of analysis, we're able to show a theorem like the following. So if you sort of take into account the contributions also from the higher order terms, you have this kind of, well, maybe somewhat negligible contribution from the higher order terms, but you have, from the lowest order, you have this Frobenius norm scaling, and you have this other contribution, which, if the marginals are close to maximally mixed, is small. And so the kind of takeaway from this is that if you have a state which is highly entangled, then these marginals are going to be close to maximally mixed. Indeed, if you want, you could recast this bound explicitly in terms of the entropies of these marginal states. So we're really just kind of casting this in terms of some measure of the entanglement of the state. If the state is highly entangled, then we get this Frobenius norm scaling for the error. And of course, if we want to simulate for long times, we can just divide the evolution up into short segments so that the total error will be small overall. And this is something that we can really control analytically. So to give you a sense of how much improvement we get from this kind of analysis, let's look at the case where we're simulating a nearest neighbor lattice Hamiltonian in constant dimensions, and we're using a p-th order product formula. So in the worst case, the scaling will be controlled by this quantity alpha that depends on these spectral norms of nested commutators. And you can show that that scales like n for any fixed p. And so the number of Trotter steps that it takes to evolve for time t is going to scale, well, it's going to scale like n to the 1 over p, basically. We can get better and better scaling with n from this contribution by taking higher and higher p. But we can compare this to what happens in the average case, right? In the average case, what we would get is this kind of normalized Frobenius norm instead of this quantity, which is going to scale like square root of n, you can show. And so we get this kind of quadratic improvement, well, in this term that enters into the error of the simulation. And so, for example, if we're looking at a first order formula, this is really an improvement by square root of n. The amount of improvement gets smaller as we go to higher orders, but it's always some, improvement that we're able to get, which is going to scale polynomially with n. And I emphasize again that this analysis is really getting kind of strictly better performance for the algorithm, but really for exactly the same algorithm. We're not changing the algorithm at all. We're just kind of for free showing that this algorithm actually performs better, by giving tighter analysis. So this, these plots show an example of what happens when you try to use this kind or consider this, average case or how close the evolution is to this average case simulation in a specific case of the Hamiltonian that's shown here. So what's shown in the pane on the left is, in blue, this is kind of the worst case performance. This is all kind of the empirical performance, not our bounds on the algorithm, but our bounds on the algorithm are close to the empirical performance. And the two curves shown here are what happens in the average case and also what happens with some particular product state input. And this is a Hamiltonian that kind of rapidly drives the state to one which is quite entangled. And so the performance is actually very close to what happens in the case where you have a state chosen at random from a one design. On the other hand, you could have some special Hamiltonian that doesn't lead the state to be highly entangled. That's sort of a non-generic thing and maybe a case where perhaps you're not so interested in doing Hamiltonian simulation in the first place. In that case, you don't necessarily see this better performance. But I guess that's OK. As long as you're getting this highly entangled state, you get this better performance. OK. So one other concern or consideration in this algorithm is maybe to think about how you can understand whether the state is highly entangled. Because, of course, this is not something that may be obvious a priori. So I think typical evolution will often rapidly produce highly entangled states. But how do we know? How can we be sure? Well, one thing you can do is you can try to sort of extract that information from the state by stopping, making a measurement, and let's say using something like shadow tomography to estimate the entanglement, specifically the kind of mixedness of these marginals that we need to use this tighter bound. And you can show that this can be advantageous even though you have to, of course, throw away the state and restart the simulation after you perform these measurements because you destroy the state. But you can show, and maybe in light of time I won't go through the details, but you can show in some specific cases that even though you have to kind of deal with this overhead of making measurements and throwing away the state and starting over, you can still get better performance as compared with only using the worst case bounds. And this analysis shows like sort of a simple case where we just make one intermediate measurement, but in principle, you could imagine a more sophisticated strategy where you make repeated measurements and really sort of adaptively estimate how much entanglement there is in the state. Okay, great. So let me try and wrap up. So what we've seen is that it's possible for simulations, product formula simulations, to perform better if we know that the state is highly entangled, which is sort of the case where we actually care about doing simulations with quantum computers in the first place. We've seen that we can sort of effectively get the performance of average case simulation, but under a more natural assumption. I discussed this procedure for sort of adaptively estimating the entanglement. So I think there are definitely a lot of interesting future directions in this area. It would be nice to have bounds on the errors that occur, the quantities that control the error in these in this work, that are sort of easy to compute and give us very tight constant factors. We have some bounds, but getting these bounds to be as tight as possible and having efficient algorithms, classical algorithms for doing the computation is maybe not always so straightforward, and that's something you definitely need in practice. I think exploring how useful this will be in practical simulations and sort of applications to chemistry and other kinds of systems would be an interesting thing to do. Perhaps we can see similar kinds of improvements, not just for real-time evolution, but for imaginary time evolution and for other kinds of processes. And more generally, I think there's a lot of scope for seeing that the performance of quantum simulation algorithms can be better than we sort of currently understand it to be by taking detailed features of the simulation into account. Okay, so I think I'll stop there. Thanks for your attention, and I'm happy to take questions.
Over multiple orthogonal states. Appreciate any comments you have on that.
Yeah, I don't have a great understanding of sort of what you're asking for, some intuitive explanation of why it is that these features help. I mean, I think it's the I think the connection between sort of the entangled case and the random state case I think is clear. So maybe the question then is why why are things better in the random case? Yeah, and I guess it's maybe because of some averaging of the errors that occurs, but I can't give you like a really crisp picture of exactly why it's the case. Sorry.
Yeah, thanks for a really nice talk. I like the Frobenius norm scaling. If I had to guess, I would have thought it would be even better. Like you just have a sum over all the Frobenius norms.
Right.
I would have thought it would be like the L2 norm of all those, because I thought they would all go in orthogonal directions.
Right.
So is that somehow the wrong intuition, or what do you think about that?
I mean, I guess maybe it is because in sort of numerical examples you can see that this scaling really is pretty close to what you see in practice. So yeah, I don't have much more to say about it than that, unfortunately.
Hey, thank you for the nice talk. I was just wondering, let's say a priori you would know both the state being simulated and maybe like the model is a Hamiltonian. Maybe you know a priori that it's like from the icing model. Do you think it could be possible to do some kind of more efficient algorithm in this case?
Yeah, potentially. I mean, I guess that's basically the last question, I mean, when can you sort of take more information into account and do better? Yeah, I mean, I think, in this analysis, we're definitely using the Hamiltonian and, some knowledge about the state, but maybe you could take more detailed features. I don't have a specific result along those lines to relate, but yeah, I think it's a great question.
Thank you for the nice talk. So, it's on?
Yeah, I think so.
So, in quantum phase estimation, any other algorithms on finding eigenvalue, Hamiltonian eigenvalue, we start with some state with the non-trivial overlap with our target eigenstate. So
right.
In practice, it is a practical thing. So, can there be better error bound for such case? Starting with the state that is close to the eigenstate of our target Hamiltonian.
Yeah, that's a good question. I mean, I think that's another problem of sort of trying to produce, let's say, ground states of systems. I mean, obviously one way of doing that is using phase estimation with a good initial guess, and the better the initial guess, the kind of more likely you will be to produce the state. So, I guess these results show that you can simulate the dynamics better, and so in that sense they can speed up those kinds of algorithms because the simulation of the dynamics will be more efficient. But I don't know of anything that sort of goes beyond that. I mean, maybe if you look more specifically at that problem, maybe that would be a nice thing to do, actually. If you look more specifically at that problem, can you show that preparing ground states is easier when those states are highly entangled? I think that would be a nice thing to think about. Yeah.
Hi. Yeah. Thanks. So I was wondering about the randomized product formula methods like QDrift.
Uh-huh.
Are there any improvements to those, or do you expect improvements in the kind of scenario that you're talking about, where you have an entangled state?
That's an interesting question. Yeah. I mean, I haven't thought of. Oh, yeah, the question was, what about sort of a randomized product formula method? So there are algorithms that sort of like choose at random what terms to apply, and you can sometimes see some improvement from that. And I guess David's asking basically, can you combine that with the state being drawn at random and get even better performance? And I didn't think about that before, so I don't think I have anything to say, but I think that's a nice idea again, and like would be interesting to see if something happens. I don't have intuition really to share. Yeah.